In part one of this talk, I introduced the quest to crack the orthographic code underlying visual word recognition, and I described how the master form priming methodology can be used to test theories about that code. I also discussed a large multi-lab form priming experiment called the FPP, and I asserted that the results of that experiment are problematic for existing models. So now, in part two, I'd like to introduce a new model. Let's start by going back to the FPP data. One thing that's clear is the cost associated with incompatible letters. The more of these letters that we denote by D, the smaller the priming effect. And something else that can be seen in the data is that inserting the different letter in the middle of the target reduces priming more than inserting it at the end. Now that difference is only 5 milliseconds, but because of the precision of the priming effects in the FPP, we can be sure that that is a meaningful difference. And I want to propose that that difference reflects the importance of letter contiguity. When we insert the letter at the end, we preserve the contiguity of the 3-4 letter pair, whereas that contiguity is disrupted if we insert the different letter in between letters 3 and 4. So with those two observations in mind, it's possible to propose a very simple model of how orthographic matching works. In this model, we simply count the number of contiguous matching letters and subtract the number of mismatching letters. To be clear, a contiguous matching letter is one that occurs in both the prime and the target and succeeds the same letter in the prime and the target. So that means that deletions or insertions or substitutions or transpositions can all disrupt letter contiguity. Now, it turns out that the cost of mismatching letters is slightly greater than the benefit of matching letters, so we subtract 1.5 for every mismatching letter. That's one parameter. To make things more concrete, have a look at the examples in this table, which all assume a 6-letter target. In the first row, we have an identity prime, 1, 2, 3, 4, 5, 6. And here we have 5 matching contiguous letters. The first letter doesn't count because there isn't any preceding letter for it to be contiguous to. And there are no mismatching letters. So the match score is 5. I'm not going to go through each of the examples in the table, but I hope that just a glance will be sufficient for you to see how these calculations are very straightforward. It's easy to see how the values in the match column here are computed. It won't be quite so obvious how the predicted priming effects in this final column are computed, and I'm not going to explain the details of this now, except to say that some very straightforward assumptions result in a simple relationship between match scores and priming effects that looks like the following graph. And there's a single parameter that determines the shape of this function, and I set that parameter based on the magnitude of identity priming. So that's 2 parameters in this simple model. So how does it do? Well, as it turns out, surprisingly well. Here, the white circles are the data from the FPP, and the red triangles are the predictions of the model. And you can see that the model does a really good job of explaining the priming we observe for a wide range of conditions involving letter additions, deletions, transpositions, and substitutions. However, that's not quite all of the conditions from the experiment. You'll remember that we also had those extreme anagram primes in which letter order is disrupted more substantially. And when we include those conditions, the model doesn't look quite so good. It shouldn't be surprising that this simple model really likes the transposed halves condition, 4, 5, 6, 1, 2, 3, because this condition preserves the letter contiguity within each half, within the 4, 5, 6, and the 1, 2, 3, and it doesn't introduce any incompatible letters. And likewise, the model overestimates these other conditions that involve misordering of the letters. So these predictive failures point to the need for just a single additional component. That is, in addition to a mismatch cost, there's also a misordering cost that's incurred when a letter occurs after a letter that should follow it. And critically, this cost isn't about letter 1 occurring in position 4 instead of position 1. It's about letter 1 occurring after letters 4, 5, and 6. That is, it's about order rather than position per se. So this addition to the simple model gives me all the key ingredients I need to introduce my new model, which I call the Sequence Predictor Model, or SPM. This model has 3 key ideas. The first, most important, is the claim that it's order rather than position which is critical, and information about order is communicated to word detectors simply by transmitting the letter signals one at a time, so transforming a parallel input into a temporal sequence. So the representation of cat is simply C-A-T. And the second key idea is that each word detector has an associated simple circuit consisting of letter receivers, one receiver for each of the letters that should be in the word. And these receivers are hooked up in such a way that activating one receiver causes excitation to be sent to the next receiver. So when the cat detector receives a letter A, the corresponding receiver sends an excitatory signal to the T receiver. And in effect, the circuit is predicting that the next letter now should be T if this is a matching word. And if that prediction is confirmed, the match score will be incremented. So that's how the model captures the benefit associated with contiguous matching letters. But as well as sending a forward excitatory signal, letter receivers also send inhibitory signals to what should be preceding letters. So for example, when the A receiver of the cat detector fires, it sends inhibition to the C. And if the letter C hasn't yet occurred, and then does so subsequently, that will result in a misordering cost. Now, on the next few slides, I have some animations of some receiver circuits. So here we're looking at the word detector for the word garden. And in this first example, the input stimulus is the word garden. And so when we have the G, that leads to a prediction that the next letter should be A. And that prediction is confirmed. That's what the filled in yellow circle denotes, which leads to the total match score being incremented. And we're now predicting that the next letter should be R, and that prediction is confirmed, so the score is incremented to 2, and so on, so that by the end of the sequence, we have 5 correct predictions and a match score of 5, as in the table we saw earlier. Now, on the other hand, suppose that we have the same word detector, but this time we have the right letters in the wrong sequence. So the input is the word danger. So we start with a letter D. That predicts the next letter should be E, but in fact, we get a letter A. This is red because this receiver has already received some backwards inhibition from the D, and so it contributes a negative input to the match score. We're now predicting the next letter should be R, but in fact, it's an N, which is sending reverse inhibition across the circuit. And then we get a G, so we have a further cost, an E, and an R. So by the time we get to the end of the sequence, we have a quite negative match score, which is associated with a greatly reduced priming effect. So when we follow that procedure for all of the conditions in the form priming project, then this is what we get. And as you can see, it's not quite a perfect correlation, but it's not very far off. So in part 3 of this talk, I'll go on to talk about how we can test this model on a new set.